Welcome to the fifth lecture of this week. Today we will do static analysis of simply supported laminate under hydrothermal load, and we will be using the Navier solution here. So, we have a laminate which is under hydrothermal load in the xy system. This dimension is A and this dimension is B, and also there is distributed load Q in the transverse direction. So, that is one cause of deformation, and there is temperature change delta T, and that is another cause of deformation, and everything is static. Temperature changes does not temperature rise does not change with time, it is fixed, and the load is also time independent. Now, these are the governing differential equations we have defined before. So, we have seen that Nx, Ny and Ns is equal to A matrix multiplied by epsilon x0, epsilon y0, epsilon s0 plus B matrix multiplied by kappa x, kappa y, kappa s, and then we have minus Nx Th, Ny Th and Ns Th. Similarly, Mx, My and Ms is equal to B matrix multiplied by epsilon x0, epsilon y0, epsilon s0 plus D matrix multiplied by kappa x, kappa y, kappa s, and minus we have Mx Th, My Th and Ms Th. And also because it is not symmetric, so we have to solve these three equations together, and because it is antisymmetric cross ply laminate, we have Axs equal to Ays is equal to Dxs is equal to Dys is equal to 0, and we have Byy is equal to minus Bxs, and we know that Bxy is equal to Bxs is equal to Bys is equal to Bss equal to 0. So, if I put all these things in these three equations, we get these three equations, and we know that epsilon x0 is del u 0 by del x and so on. So, this becomes our governing differential equations for this problem. Now, we know that if Nx, Ny, Ns under the thermal and moisture effect is equal to summation k is equal to 1 to n zk minus 1 zk. We have Q matrix for each ply in the xy system, and alpha x for kth ply, alpha y for kth ply and alpha s for kth ply dz, and it is multiplied by delta t. Now, since it is cross ply laminate, so each ply has orientation either 0 or 90. So, in that case alpha s is equal to 0 for each ply, and similarly Qxs and Qys are 0 for each ply. So, alpha s for kth ply, Qss for kth ply, Qys for kth ply is 0. That is why we will see that NSTH is equal to 0. So, this quantity is 0 and this quantity is 0. Similarly, if we look at the definition of the hydrothermal moments, the definition is k equal to 1 to n zk minus 1 zk z into q matrix in the xy system for the kth ply alpha xk, alpha yk, alpha sk, and we have here the effect of both temperature and moisture. So, let us write it fully. So, it is into delta T, delta T, delta T plus beta xk delta H plus beta yk delta H plus beta sk delta H dz, and here we have delta T, delta T, delta T plus beta xk delta H plus beta yk delta H and plus we have beta sk delta H dz. So, again these quantities are 0. So, this also tells us that MSTH is equal to 0. So, this quantity is also 0. Now, let us look at the boundary conditions. So, it is a simply supported laminate. So, all the 4 edges are simply supported. So, at all the 4 edges we have W, the displacement along Z equal to 0, and also the support is such that at the x face it allows displacement along x, but does not displacement along y. Similarly, at y face it allows displacement along y, but does not allow displacement along x. So, at x equal to 0 we have W is equal to, at x equal to 0 and A we have W is equal to 0, at x equal to 0 and A we have V0 is equal to 0, and at y is equal to 0 and B we have W is equal to 0, and y is equal to 0 and B we have U0 is equal to 0. So, these are all essential boundary conditions, and then at x equal to 0 and A we have Mx equal to 0 and Nx equal to 0, and at x equal to y equal to 0 and B we have My equal to 0 and Ny equal to 0, and these are all natural boundary conditions. Now, we have to assume something for the solutions. It should satisfy both the essential and natural boundary condition, and also the assumption should be such that I have trigonometric term or a common trigonometric term coming out from each equation. So, U0 is assumed as this summation of m going from 1 to infinity, n going from 1 to infinity, capital Umn which is unknown in the problem, into cosine m pi x by a sin n pi y by b. Similarly, V0 is summation m equal to 1 to infinity, n equal to 1 to infinity, capital Vmn sin m pi x by a cosine n pi y by b, and W as a function of x y is, it is also a function of x y, that is summation m equal to 1 to infinity, n equal to 1 to infinity, Wmn, then sin function sin m pi x by a sin n pi y by b, and also we assume the load Qxy also in the form of a trigonometric series, and this becomes this we can write as Qmn sin m pi x by a sin n pi y by b, and also we write the temperature change delta T as summation n equal to 1 to infinity, m equal to 1 to infinity, Tmn sin m pi x by a sin n pi y by b, and delta H change in the moisture level as again double summation m equal to 1 to infinity, n equal to 1 to infinity, Hmn into sin m pi x by a sin n pi y by b. Now, we know that qmn can be written as 0 to b, 0 to a, we have q sin m pi x by a sin n pi y by b dy dx divided by 0 to b, 0 to a sin square m pi x by a sin square n pi y by b dy dx. Now, similarly, we can write Tmn and Hmn also. So, similarly, Tmn and Hmn can be expressed. So, Tmn, Hmn, Qmn, everything is known to us. What is not known to us is Umn, Vmn and Wmn. Now, if I put all these approximations in these 3 differential equations, then those 3 differential equations take this form. So, the first differential equation, so let us just write them. So, this we can call equation number 1, equation number 2, equation number 3. So, equation number 1 takes a form like this: n equal to 1 infinity infinity, m equal to 1 to infinity, something multiplied by cosine m pi x by a sin n pi y by b equal to 0. And then equation number 2 takes this form: n equal to 1 to infinity, m equal to 1 to infinity, something multiplied by sin m pi x by a cosine n pi y by b equal to 0, and this becomes n equal to 1 to infinity, m equal to 1 to infinity. Again we get sin m pi x by a and sin n pi y by b outside. Now, we know that these trigonometric functions, they cannot be 0 everywhere. So, these expressions to be 0, every term inside the bracket should be separately 0. So, this equal to 0, this equal to 0 and this equal to 0. So, for each combination of for each m and n, we get 3 equations. So, for each m and n, we get 3 equations, and those equations are minus ax m square pi square by a square umn minus as n square pi square by b square umn, and then we have minus axy plus as mn pi square by ab vmn plus we have bxx m cube pi cube by a cube wmn, and then minus we have mn m pi by a Tmn into alpha x for the kth ply, qxx for the kth ply plus alpha y for the kth ply, qxy for the kth ply, and this gets summed over k is equal to 1 to n all the plies and multiplied by Tk. Tk is the thickness. Tk is the thickness of each ply. Similarly, for the moisture effect we get m pi by a h mn summation k equal to 1 to n. We have beta x for kth ply, q x x for kth ply plus beta y for kth ply, q x y for kth ply into T k, and that is equal to 0. So, this is the first equation that we get, and then we get minus mn pi square by AB AX plus AXY plus ASS into UMN minus ASS m square pi square by A square VMN minus AYY n square pi square by B square VMN. Then we have minus BXS BXX n cube pi cube by B cube WMN, and then we have those terms coming from the thermal and moisture effect. Alpha x for the kth ply multiplied by qxy for the kth ply plus alpha y for the kth ply multiplied by qyy for the kth ply into Tk. Tk is the thickness of each ply, and here actually Tk is equal to T is equal to thickness of ply. So, we are assuming that each ply has same thickness. So, Tk is equal to T minus we have n pi by B h mn, then we have k equal to 1 to n beta x for the kth ply qxyk plus beta y for the kth ply qyy for kth ply into Tk, and that is equal to 0. So, from the last equation we have minus m square dxx into m to the power 4 pi to the power 4 by a to the power 4 plus 2 into dxy plus 2 dss into m square n square pi to the power 4 by a square b square plus dyy n to the power 4 pi to the power 4 by b to the power 4, and then we have minus bxx into m cube pi cube by a cube into umn minus n cube pi cube by b cube into vmn, and then we have minus m square pi square by a square Tmn, then k is equal to 1 to n alpha x for the kth ply into qxx for the kth ply plus alpha y for the kth ply into qxy for the kth ply multiplied by zk minus zk square minus zk minus 1 square by 2 minus we have n square pi square by b square into Tmn into summation k equal to 1 to n alpha x for the kth ply, qxy for the kth ply plus alpha y for the kth ply, qyy for the kth ply multiplied by zk square minus zk minus 1 square by 2, and then we have m square pi square by a square, the same quantities for the moisture effect, k equal to 1 to n alpha beta x for the kth ply into qxx for the kth ply, beta xk qxxk plus beta yk qxyk zk square minus zk minus square 1 square by 2 minus n square pi square by b square hmn, and then we have k equal to 1 to n number of plies, beta x for the kth ply multiplied by qxy for the kth ply plus beta y for the kth ply multiplied by qyy for the kth ply multiplied by zk square minus zk minus 1 square by 2, and then we have minus qmn equal to 0. So, we have 3 sets of equations, we can name them equation number 4, 5 and equation 6. So, we can solve equation 4, 5, 6 and we can find out solving equations 4, 5, 6, UMN, VMN, WMN can be obtained, and if I get UMN, VMN, WMN for each Mn combination, and then we can put it in the approximation back and we can get our solution. Now, one thing to note here is that if ns here was not 0, then I would have got a sine cosine term instead of cosine sine term in the first equation. So, in that case I could not separate the trigonometric terms. So, in that case our Navier's solution would not be possible. Now, let us look into this example. Here we have simply supported antisymmetric angle ply laminate. We have seen before that when there was no effect of moisture or temperature, we could solve this problem using the Navier's solution approach, but here in the presence of these factors we cannot have that kind of solution, and we will see that why. We will see why it is so now. So, here these are the differential equations, governing differential equations. Now, because it is antisymmetric angle ply, so we have A x s is equal to A y s is equal to d x s is equal to d y s is equal to b x x is equal to b y y is equal to b x y is equal to b s s is equal to 0. So, in B matrix the non-zero terms are b x s and b y s, and then if we put these approximations we get these 3 governing differential equations. Now, previously we had NS0, NSTH0, NSTH0 and MSTH0, but we do not have those terms 0 here, because each ply has BXS, BYS non-zero and also alpha S is non-zero. So, BXS, BYS, alpha S, beta S are non-zero, and this implies that NS not equal to 0, MS not equal to 0. Now, let us look at the boundary conditions. So, we used this kind of boundary conditions before. So, here these are the essential boundary conditions, and these are the natural boundary conditions, and with these boundary conditions we had these assumptions. Now, these assumptions satisfies these boundary conditions, they say, but if we put this in the actual equation, we will see that we cannot have the trigonometric terms, common trigonometric terms coming out. So, these assumptions now not suitable for Navier type solution. So, if we, for example, in the first equation, if we put these assumptions, we get a sine cosine term here, because u0 is umn sin m pi x by a cos n pi y by b. So, if I differentiate that twice with respect to x, I get sine cosine terms. Similarly, if I differentiate u0 twice with respect to y, I get sine cosine terms. So, I get sine cosine terms here, sine cosine terms here. V is cosine sine. So, if I differentiate once with respect to x, once with respect to y, I get sine cosine terms here. W is sine sine. So, if I get differentiate twice with respect to x and y once with respect to y, I again get sine cosine terms here, I get sine cosine terms here. But here our delta t, if we assume delta t as Tmn sin m pi x by a and sin n pi y by b, similarly, if we assume delta h like we did before, n equal to 1 to infinity, m equal to 1 to infinity, Hmn sin m pi x by a sin n pi y by b, then this term is a cosine sine term. We will get cosine m pi x by a sin n pi y by b here, and this would remain a sine cosine term. So, because of this term, I will not be able to separate out the trigonometric functions. Similarly, here we will see the same thing. So, this will become cosine sine, cosine sine, cosine sine, cosine sine, cosine sine, and then this will be cosine sine, but this will become sine cosine. Similarly, here this will give me a sine sine term, sine sine term, sine sine term, and then we will have here we will also will have the same thing, sine sine term, sine sine term, sine sine, sine sine, sine sine. Here also we have two sine terms, but here this term will give me cosine and cosine term. So, again because of the presence of this, we will not be able to separate out the trigonometric terms. So, for this kind of problem, a Navier solution is not possible. So, the way out is energy or virtual work based solution, energy or virtual work based solution. So, for that we have to incorporate the hydrothermal effects in the expression for stresses and use the energy or virtual work equation. After that the procedure is same, only thing is that in the stress expressions the effect of hydrothermal effect has to be incorporated, and we have seen the stresses how they look like if we have the hydrothermal effect incorporated. So, if we do that, again follow the systematic procedure that we have discussed before in last few weeks, we can get a set of linear algebraic equations solving which we can get the unknowns in the problem and we can have our solution. So, this brings us to the end of this lecture. Thank you.